Section 7.1, Area of a region between two curves. In this section, we'll be reviewing the area found between two curves. So obviously, we're going to be using definite integration to find the area under a curve, but in order to find the region here bounded between two curves, we're going to combine actually two areas. So first off, we're going to look at the area from basically the outside all the way down, and then we'll subtract the area found in here. So by kind of doing two different areas and subtracting them, we can find the area common that's bounded by these two curves. So the way you want to look at it is in dx, when we have our up and down rectangles here with an x value as a width, is to think of our top function, right? That gives us the overall height here, minus the bottom function here, that is the part we want to get rid of. Now, because obviously both those functions that determine the top and the bottom of the rectangle share limits of integration and variable, we can put them together in one integral. Now, when we set these up, clearly I'm okay with using the calculator for a lot of these problems, but be prepared also to do them without a calculator. So don't forget how to do the fundamental theorem of calculus and evaluate your antiderivatives using those limits of integration. So let's try an example. So we have y equals x plus 6 and x squared. So the first thing we want to do is to make a quick sketch so we can see exactly where our region is. Now, aside from that, we also want to know what function makes up the top and bottom so we can set up the integral correctly. So in this case, obviously, if we look at x plus 6, that's just going to be a line with a slope of 1 passing through 6. So it's going to look something like this. So I'm going to label that my x plus 6 right here. And then when we look at x squared, that's clearly going to be the parabola that kind of comes down through the origin and goes up this way. So if I label this y equals x squared, now we can see the region that's bounded by those two things. So we're looking for this kind of area right in here. Now, if we want to go ahead and draw our rectangles in, the rectangles would look something like this. Okay, just give us a little visual cue on what the top and the bottom is. Okay, so clearly on this interval, the top is going to be the line x plus 6, the bottom is going to be the parabola x squared. So when we set up our integral, we're going to be integrating along the x-axis, obviously, and along the top again being that x plus 6, and then we'll subtract from that the bottom x squared. Now, the last step is to make sure we have our right limits of integration. So this region, obviously being bounded by these two curves, is going to start and end at their intersection points. So it's going to be our job to set them equal to each other and solve. So our job is to figure out where is x squared equal to x plus 6. Now, clearly when you do this, you can go ahead and solve and move things around and figure out where that's going to be. So here, if we solve for 0, we can then factor. And this is obviously going to be like -3 and positive 2. And so because of that, we can see that this right here is going to be at -2, and this x value is going to be positive 3. So that tells me what our limits of integration are going to be. Now, again, at this time, this is a pretty basic problem. I would expect you to be able to do this by hand. However, for many of our problems in here, we'll go ahead and just use our technology to make it easier. But again, especially with the AP exam, on any non-calculator section, be prepared to work this out, find the antiderivative and evaluate those limits of integration. So in this case, if we go ahead and use our calculators and punch it in, we're going to get 125/6. Now let's review finding the area where we use dy. So in this case, we again have a region bounded by two curves, but this time we're going to let our rectangles run horizontally. So their vertical width here, kind of going up and down, is what we're looking at as far as the dy. So in this case, because we're dy, we're going to be using limits of integration of their y values from bottom to top. Now, everything else is basically the same, right? We're going to find our points of intersection, look where the region is. It's just important this time that instead of thinking of top and bottom, because our rectangles run horizontally, we want to follow the right minus left rule for dy. So we're going to take basically the area here bounded on the right side, wherever that curve is, minus that curve on the left side, because that, of course, is how we're going to measure this distance. So again, for example, let's look at this right here. We have x equals 4 minus y squared and y equals x plus 2. Now, if you notice, this one's already solved for x in terms of y. So obviously, if we're going dy, that's very helpful. This one's not. But a lot of times you may see this because this may be easier to graph this way and this may be easier to graph this way. So don't expect your equations always to be solved for the variable you need. Oftentimes, they may be written away to help you graph them. So if we come up with a picture to see what this looks like, okay, we have our x and y axis here. Now, if you look at the 4 minus y squared, that's obviously going to be a parabola that faces sideways. But because this is negative, it's going to be opening this direction toward the left, and it's also going to be shifted over 4. So that means when I sketch this, it's going to be that parabola shifted over 4 opening to the left. And then looking at the other line, it's just y equals x plus 2. So if I make this a little bit longer here, that's just going to be a line that passes through 2 like this. So the region bounded looks something just like this. Now, obviously, again, we're going to need to find our limits of integration by finding these intersection points. Now, to do that, we want to right away convert this one over to x equals. So when we do that, that's going to equal y minus 2. Okay, so for the rest of the problem now, we want to go ahead and use this when we talk about this this line right here on the left, because again, we're going to have all our variables agree. We want to be in dy, so we want to make that happen. So in order to find our limits of integration for our y values, we're going to set the 4 minus y squared parabola equal to our line y minus 2. So if you set this equal to 0 and factor and so on, we'll discover our limits of integration go from -3 to +2. So when we set this up, we're going to integrate along our y-axis from -3 to 2, always in that increasing way. And then, of course, our right side is going to be, again, the parabola here. And then our left side will be the line. So we'll just take our parabola minus the line. Now, unlike our previous example, both of these terms have multiple things going on. So I think using parentheses, especially in the subtraction, is going to be important. So don't forget to do that. So our parabola on the right side here is going to be our 4 minus y squared. And then we're going to go ahead from that and get extra grouping symbols here, subtract our y minus 2. And again, it's very important, especially around the y minus 2, we get those parentheses, so that sign goes to both of them. Now, looking at this, again, this is one you should be able to do by hand. This is a pretty easy antiderivative, and you can evaluate those limits of integration. But when you plug this into your calculator for the area, this one's going to work out to, again, be 125/6. Now, one of the things that comes up when we look at, finding those regions that are bounded by curves is oftentimes having multiple intersection points. Now, this can be a big deal because, as you can see in this situation here, in this region that's bounded and this region, they don't have a common top and bottom. In the left-hand region, it's going to be the black graph here. Okay, this is the cubic graph on top, whereas the gray graph, this quadratic, is on bottom. But when we move past to the other part of it, right, the other part of the region bounded by the curves, now the parabola becomes on top and the cubic is actually on the bottom. Now, the most important thing when setting these things up is following that top minus bottom idea when dealing with dx. And again, looking at these equations, clearly we would have to, have dx be our variable that we're going to integrate with respect to. So the one thing I can't adjust is I have to go top minus bottom. And so because the top and bottom change from one region to the next, it forces me to use two integrals. So we're going to use one integral for the left region and then add a second integral to find the area here that's in the second region. So on this setup, we don't need to worry about drawing it or finding intersection points. That's already been done for us. We just want to make sure that we get the right limits of integration and get the right equations in the right place as far as top and bottom. So let's start with the left region over here. This is going to go from -2 to 0. So those will be our limits of integration along the x-axis. The top, again, is the cubic. So we're going to take the 3x to the third minus x squared minus 10x. And then we subtract from that the quadratic, okay? And again, I need to put this in parentheses because we need to subtract both of those pieces. Now, if you don't want too many sets of parentheses, clearly, as you do this, you could just distribute and call this, plus x squared minus 2x. But I just want to emphasize this is the top and this is the bottom. But now what we want to do is we want to add to that, and I'm actually going to write below it because I'm running out of space, but we're going to add to that the integral for the region here. So the second region on the right starts at 0 and ends at 2 along the x-axis. So that will be my limits of integration. And because it flipped, now the top is a quadratic, the bottom is going to be the cubic. So this time when I set this up, we're going to take our -x squared plus 2x and then subtract the rest. So in this case, we have our 3x cubed minus x squared minus 10x. And again, I'm putting that in parentheses just to make sure it gets put in the right place. Now, of course, from here you can work it out whether you do it by hand or a calculator, but my emphasis is just the idea that, when you have a region, right, that actually ends up having two different parts to it. When you look at the curves and things that are bounds, you might have situations like this where the top and the bottom flip. So again, the top, bottom, and if you're in dy, the right minus left is the one pieces you can't adjust or change. You have to follow the top minus bottom, right minus left rule. So if it does require you using two different integrals, that's what you're going to have to do. Now, another situation that comes up is symmetry. Now, the nice thing about symmetry is, just like before, sometimes you have these two regions, and again, like our last example, you can see the top and the bottom change. In the bottom region, the top is the cubic and the bottom is the linear. However, it switches to a line on top and the cubic on bottom up in the region above. However, since we know this graph is symmetrical, right, then, with that knowledge, we could simply kind of make our lives a little easier by just finding one region and then doubling it. Okay, you're definitely allowed to do this. Now, you don't have to do this. Just like our last example, you definitely could set up two different integrals. But in a situation like this where we know the symmetry exists, it can save time and give you an easier integral to calculate, especially if you're doing it by hand. Okay, so on this one, let's just go ahead and let's just find the bottom one, and then we'll just double that. So looking at the bottom region, we're going to be going from 0 to 1 as far as the amount of the x-axis. So when we set this up, we're going to integrate from 0 to 1. And since I'm using the bottom one, we'll let the top be the cubic and the bottom be the linear. So this will start with our cubic, which is going to be our x minus 1 cubed, minus the bottom, which is x minus 1. And again, if we just go ahead and throw a 2 out there and double that, that's going to allow us to basically take this region, double it, and obtain the entire thing. And again, if you wanted, you could clearly find the region up here on top from 1 to 2, where you take the line minus the cubic and double that. Or, again, if this isn't your thing, just like our last example, you could just find the two regions separately.